Hello, this is much more than problem 2. I want to do a review of several concepts that are extremely important for you to keep in mind, and that way you'll see that problem number 2 is relatively easy. So the first concept that I want to review is the force vector directed along a line, and basically this is a situation in which you have the magnitude of a force, but whenever you want the vector, because you don't have the vector, then you have to use a position vector r and divide it by its magnitude, so that then the magnitude of the vector in any direction, and in this case you have this f multiplied by the unit vector in this direction. So if it's this, then it will give you the force vector in that direction. So for example, let's say that you have this problem, the 420 Newton force along cable AC, and it's going in that direction. You know that direction, so you need to get the force vector, because especially in 3D, we need to work with the vectors. So the first thing you need to do is to look for the position vector in the direction of the force. So in this case, the force goes from A to C. So the vector A to C would be vector C minus vector A. And what we need to do is to find these coordinates, so that then we can talk and mention specifically what is the vector. So let me look at my notes here. So for coordinates in point C, you have in X, and remember, this tells you what is the positive direction. So for C, the X is 2, the Y is 3, and they're positive, and the Z is 0. Now those are the coordinates, but the vector C would be 2I plus 3J plus 0K. Now let's take a look at coordinates A. So point A, in X we have 0, in Y we have 0, and in Z we have 6. So vector A is 0I plus 0J plus 6K. Now remember, we can just say that this is 6K, and we can say that this is just 2I plus 3J. But we want to make sure that you understand what are the I, J, and K components. So the vector, position vector C minus position vector A gives me the position vector from A to Z, and C, not Z. So RC, so I have 2I plus 3J plus 0K minus, in A would be 0I, and I put it like this because that way you have less chance of making a mistake. So RAC is going to be 2I plus 3J, and then 0 minus 6 minus 6K. So it's this. Now, I need the unit vector in that direction. UAC would be that vector AC divided by its magnitude. And so here I have 2I plus 3J minus 6K divided by, and then the magnitude would be 2 squared plus 3 squared plus 6 squared. and this would be then 2 over 7i plus 3 over 7j minus 6 over 7k. So this is my unit vector in the direction AC, and my force goes in that same direction. So my vector would be that magnitude AC multiplied times the unit vector AC. So this would be 420 times 2 over 7i plus 3 over 7j minus 6 over 7k, and this of course are newtons, so my vector is 120i plus 120j minus 360k, and of course these are newtons. So that's the first thing. So remember, whenever you don't have the vector but you have the magnitude, you look for a vector in the same direction of the force, find the unit vector, and then multiply the unit vector times the magnitude to get that force vector. Okay? So here is the problem in a better, nicer, handwritten form. So now we're going to talk about the projection of the vector, which is different. And in the case of the projection of the vector, we have, in this case, and this should be also a vector. So what we have is, we want the magnitude of the projection of the vector along a line specified by this unit vector. So let's see what is the definition of a dot product, and it can be the magnitude of A, B times cosine of theta, but this you have to know. If you don't know it, then you go to this. So A dot, and that's the way it's read, it's not multiplication, it's going to be equal to AX BX plus BY AY BY plus AZ BC. A dot B equals the same as B dot A. So it's commutative. Okay? So this would be the definition for finding that angle, but I want to explain it with an example. So let's say that I have this problem, and I have here my force vector because I already have the magnitude and the direction. And now what I want to know is, what is the force or the magnitude of the projection of the vector along this line that goes from A to 0. And this is a very important concept whenever we have to choose the type of material, or we want to see the forces that are exerted. Remember, it's like when someone pulls you from one place, you will feel those forces in other places. Like when you work out and realize you have muscles that you didn't know you had. So that is the goal of this discussion, that you will see how forces are projected onto other surfaces, not necessarily in that same direction as the force. Okay? So what we need to do in this case is, and let me see if I have, so you have to find the vector, position vector from A to 0. And so the force from A to 0 is the dot product of the force, and this is a vector, dot RA0. So let's do this first part. So for A, my coordinates are in X, and remember this is X, Y, and this is C. In X, my coordinates of point A is 1. In Y is negative 2. And in Z is 2. I think that is correct. We'll see here. And then for 0, of course, it's 0, 0, 0 for that point. So when I look at my vector from A to 0, then it's R0 minus RA. And this is important to write because this can be a game changer. So R0 minus RA. So here R0 would be 0I plus 0J plus 0K. And then here my RA would be 1I minus 2J plus 2K. So R0A is R0 minus RA. So I have here J plus 0K. And look at this. Minus. And then you have 1I minus 2J minus or plus 2K, which then changes now to, I have minus 1I plus 2J plus 2K. And remember now, this is meters. I didn't put it earlier. So then my projection of that vector along this line, so this is the equivalent of like the component x and y if you were looking for x and y, but now you're not looking for a projection on x and y, you're looking for a projection somewhere else that's not necessarily xy. So then the solution for this would be then my force projected, and this is a magnitude, okay, it's F dot RAO, okay, so it would be here's my force vector. So I have minus 6 minus 1 plus 9 times 2 plus 3 minus 2, and this is 18 kilonewtons. So that is the magnitude of the force. But what if I asked you, I don't want the magnitude, I also want the vector? Well, then you follow what we did in the previous example. So if I have the vector RAO, then I need the unit vector in that direction, which would be minus 1I plus 2J plus 2K divided by its magnitude, okay, and this would be UA0, and I don't have the answer for that right away, and I don't want to make you wait, but then this here would be then my force vector, which would be the magnitude, which is 18 kilonewtons, right? And then you have minus 1 square root of 9 plus 2, sorry, let me fix this. Yeah, plus 2 divided by square root of 9, J plus 2 square root of 9. Okay. And this is the force vector AO. So now we have combined the two concepts, the concepts of the force along a line and then a force along a projection different than XY. So this is a little nicer established here, and then in this case, if you wanted to know what is that angle, then you can find it. Okay, so now let's talk about the cross product. And remember, the cross product is to determine the moment of a force in 3D, because in 2D we just do it in scalar, and then we say, okay, the sum of the moments, and we talk about the positive or the negative, but in 3D it's not so easy, so we use the cross product. And the moment of a force about point A would be R cross F, where R goes from the position where you want to calculate the moment, and it's going towards the force. And remember, it doesn't matter whenever you use the cross product. It can be any point from that point to any point along the line of the force, and that is the cross product. And the cross product, the thumb, the right hand rule, gives you the direction of the moment. And what's important here is that in the case of the dot product, it was commutative, but in the cross product is not, because it gives you a negative number whenever you switch directions. And this goes from A to B, and this is your thumb, so that gives you the direction of the moment. And then this is from B to A using your fingers, and gives you a negative C. So if we look at the cross product, you obtain all these are bold, so these are vectors. Okay, so calculating the cross product, then you do the determinant ijk, ax, ay, ac, bx, by, bc. But remember, the cross product is what? R cross f. So then you have here rx, ry, rc, and then here you have fx, fy, and fz. Okay, and remember how it's solved. Here you have the I, and then you have a negative number, so you should remember that. And if you don't see it well, then let me just erase this here, and you can pause the video and make sure that you have that correct. Okay, so in the case of the cross product, like I mentioned, then I'm not going to do this problem, but let's say you have to calculate the moment of the force about point A. So you can go from point A, find this R to C. So the moment about A here would be, and this is a moment, what it gives you is R from A to C cross F. And then here you have a magnitude, so you would have to find the force multiplied by the unit vector in that same direction to have the force vector. So remember that this is a vector. So if I asked you what is the magnitude, then so this would give you maxi plus mayj plus mazk. So the magnitude would be max squared plus may squared plus maz squared, and this would be the magnitude of that vector. So I hope that is clear. Now we're going to see the analogy of a projection of a moment across an axis that is not necessarily x and y. And so it's the same concept as the projection of a force along a line that is not x and y. So you have your moment, and let's say that you want along a line that is AA. So the first thing you have to do is to compute the moment of the force to have that value. And then once you have the moment of the force, then the same way that we looked at the magnitude of the force, like we had this FA was the same as the F dot UA. If you don't remember, go back to the third or fourth slide from this presentation. So the case for the moment is the same. Now we're going to use the same concept, and remember that what you get here is a magnitude. Okay? So the first thing you do is calculate the dot product, or the cross product, I should say, and then you apply the dot product for the projection. Okay, so you do cross R cross F, and then you calculate the moment, and then the projection of the moment along line UA. And remember, this is not bold here, so it's magnitude. So you can do it in 2 steps, but you can also do it in 1 step, and that's where the triple scalar product. So instead of doing it the R cross F first and then do the dot product for UA, you can do it directly like this. Okay, so, and the rationale is the same in the sense that then you do UAX and then you have RY FC minus RC FY, and then you have a minus sign here, UAY, okay, and then you have RX FC minus FX RZ, and just check my calculations in case that there's a mistake, but I think that you're getting what I am saying. RX FY minus RY FX. So whenever we do the triple scalar product, it's a magnitude because it's a dot product here. So here you get a vector, but here you have the vector, but then because it's a dot product, this is a magnitude. So I hope that explains good. So let me just show you this particular example. So what I did here was this force, I already have it here in vector form. So if I look at this force that it's equal to 200 newtons has to be equal to the square root of that 100 square plus 100 square plus 141.4 square. Okay, so it's related, right? And you should remember that. So let me erase it, and remember you can pause this anytime. So here I have the force, and so the question is, what is the magnitude of this force about the x-axis? Okay, so we do first the cross product from any arbitrary point. It's always good to do it from here. So we'll do the cross product, R cross F, and then you can do the dot product, which is here, and this would be here with UX because in this case it's along the X, so this is the vector 1I, and then it's 0J, 0Z. Okay? So let's do this. So I have here and I don't want to go over the position vector, so that's why I'm showing this. So the position vector from 0 to A, which is this point where the force starts here. So I use this point along the force. So this is my vector ROA. It's this vector here, 0I plus 0.3J plus 0.25 K meters. This is my force vector, okay? And so we're looking at the projection along this. So this is the unit vector in this direction. So I will find the magnitude of the vector, and this should say x because it's along the line x. And so this is solved. Remember that I put this here because this is the vector along which you want to look the projection. So it was 1, 0, 0, and then the R, which is the position vector here, is in the second line, and then of course the force vector. So this gives me the magnitude of the vector. Now, what if I want the vector? Remember, this is the magnitude, but the vector, then it's the same thing as before. So if I have this magnitude of the vector, and I multiply times that direction of the vector, okay, then it will give me the vector for that moment. So in this case, I have 17, and in this case you need to be careful because whatever sign you get here also will define your vector. So 17.4 is the vector, but then I want it in this direction, 1I plus 0J plus 0K. Okay, so this is then, and this is of course in Newton meters. This is Newton meters, which is here. So in this case the vector is 17.4 I Newton meters, which makes sense because I had only the I, but if I had a different vector that was not I, this would be the case. Okay? So having said that, let's do problem 2. Finally, we're getting to problem number 2 of the exam. So the first question is, which of the following equation correctly evaluates the scalar triple product of 3 Cartesian vectors r, s, and t? The first thing you need to remember is that because it's a triple scalar product, this is a dot product, so this c and c are eliminated because these are vectors. So I need to choose between these two. So if I have this here, then I look at my answers and I see, okay, well, there's a plus here and that doesn't make sense, but let's see. So what we have is, if you have Rx, Ry, Rc, and then Sx, Sy, Sc, and this was given in the exam, and then you have Tx, Ty, and Tz, right? So we do Rx, and then this would be Sy, Tc minus Sc, Ty, and then you have a negative here, so it would be Ry minus Ry, and then I have Sx Tc minus Sc Tx, and plus Rz, and then you have Sx Ty minus Sy Tx. So whenever we look, then the answer is A. Okay, so this put the answer B into question, so that's it. So now the next question is, using the position vector from A to C, calculate the moment about segment AB. So I'm telling you which projection I want. Okay, so I'm going to calculate the vector. This would be like the moment about point A, right? I'm going to calculate this, but then look at the projection. So this puts together everything that we have learned. Okay, so, oops. Something happened here, I apologize. Okay, so what we're going to do is then have this vector calculated. But remember, first we have to calculate the magnitude of the vector. So if I have coordinates, so I need coordinates in A, B, and Z. Okay, let me erase this here so that didn't work. Okay, so I have coordinates A, which are of course 0, 0, 0. I have coordinates B, which are 1.4 in X, 1.8 in Y, and 0 in Z. And then I have coordinates C, which are 1.4, 1.8, and 1.6. So I'm going to look at my vectors, and my vector B would be 1.4 1.4i plus 1.8j plus 0k, and then my vector c would be 1.4i plus 1.j plus 1.6k. Okay, so my vector from A to C would be RC minus RA, okay? And so that vector RAC would be 1.4i plus 1.8j plus 1.6k. And my vector from A to B is going to be RB minus RA, which is going to be 1.4i plus 1.8j plus 0k. Now, I'm going to go a step ahead and do the U in the direction of A and B, okay? Because then this will be 1.4i plus 1.8j divided by its magnitude, which is the square root of 1.4 squared plus 1.8 squared. Let me just put it, want to make sure I leave everything in the same page so we don't have to change it. So this would be like 2.28. Okay? So I can do the RAC cross F, I already gave you the F, and then this would give me the moment about A, and then if I want the projection along AB, then I do the dot product. This is the vector MA dot UAB. But I'll do it in one step with a triple scalar product. So the magnitude AB is going to be UAB dot R, and this is RAC cross F, and these are vectors as well. So this would be 0.614, 0.789, and 0, and then 1.4. So this is what's here. 0.614i plus 0.78j. So the numbers are approximate, but 1.8, 1.6, and then minus 250, which is the force, 60, and 165. So whenever you solve this determinant, the magnitude is 374.45. It's the negative, so in this case it gives you a magnitude but also a direction. So, but that's a number. I want the vector. So then I go, this is the magnitude AB, and then that goes in the direction, unit direction AB. So then I have 230i minus 295j. This is the vector. Okay, so I multiplied this. This is UAB, and then times this number. Okay, so I hope this helps. And this was the most challenging one because it put together everything. So if you know how to do this, then you understand everything up to this point, which is chapter 5. Okay, or end of chapter 4, I think. So thank you very much. Hope this helped. Bye.